Hello and welcome to Ot Math. In this edition of Ot Math, we're going to talk about solving right triangles. This is chapter 9.1. All right, so we're going to review and expand trig function relationships. We're going to talk about inverse trig functions. We'll talk about using trig to solve right triangles and what it means to solve a right triangle. And then we're going to use trig to solve real-world problems. All right, so just to review our trig ratios: sine, cosine, tangent, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Remember SOHCAHTOA: sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite over adjacent. And then now we're going to talk about the reciprocal relationships of cosecant, secant, and cotangent. So cosecant is just the reciprocal relationship to sine. So instead of opposite over hypotenuse, which is what sine is, the relationship of those two sides, now it's the hypotenuse over opposite. Secant is hypotenuse over adjacent, so the reciprocal of cosine. And cotangent is the reciprocal of tangent, which is adjacent over opposite. So I like to say that in any of the two pairs, one pair always has to have one co. So sine cosecant, cosine secant, tangent cotangent. All right, so let's take a look at how that plays out for sine A, B, and C. Sine of A, 3 over 5, B, 4 over 5. Sine C, 5 over 5. Tangent A, 3 over 4, so opposite over adjacent. Tangent B, 4 over 3. Tangent C, 5 over 0, which is undefined. Cosine A, 4 over 5. Cosine B, 3 over 5. Cosine C, 0 over 5. And so we just see that the value that we get for any trig function is based on the angle that's in question. There's no value that's set for any given letter of A, so to speak. So cosine of A is going to be most likely different from cosine of B, given that the two values are, two angle measures are different. So we're just talking about relative to a given angle, what is the relationship of the side lengths? All right, so cosecant of A, remember, is reciprocal of sine. So cosecant of A will be 5 over 3. Sine is 3 over 5. Cosecant of B would be 5 over 4. Sine of B is 4 over 5. Cosecant of C is 1. So let's think about these values. You can see the values are 1 or greater, and that is the reciprocal of the value that we get with sine. So with sine, we know that the values always have to be between 0 and 1, or the absolute value has to be between 0 and 1. With the reciprocal values, both cosecant and secant, you realize that the values always have to be 1 or greater, because the length of the hypotenuse always has to be the same as the side length or greater in that right triangle. All right, so secant is a reciprocal relationship for cosine. So secant of A, 5/4, secant of B, 5/3, secant of C is undefined. Right, cotangent of A, again, reciprocal relationship for tangent. So now adjacent over hypotenuse, 4 over 3 for cotangent of A. Cotangent of B is going to be 3 over 4, and cotangent of C is 0 over 5, or 0. All right, so now we're going to review our inverse trig functions. This should be a quick review for you. So we started by talking about saying that the sine, cosine, or tangent of some angle measure tells us what the relationship ratio is of one side to another. So now, let's use the 30, 60, 90 triangle, and admittedly this is a bad right triangle. It's not really drawn to scale, and this definitely doesn't look like a right angle. Though I'm saying it's a right angle here. Sine of 30 is going to be the opposite over hypotenuse, so x over 2x, or 1/2. Sine of 30 is going to be 1/2. Now, we can also think about the relationships in a different way. We can say, all right, given the side length relationship of opposite to hypotenuse is 1/2, what is the angle measure? So that's what the inverse trig function does. The inverse trig function of a side length relationship is equal to a given angle measure. And here we can say inverse sine of 0.5, or 1/2, is equal to 30 degrees. So that's how we use our inverse trig functions to find and the angle measure. And also, you could get an output in radians, so please make sure that your calculator is set to the correct value for whatever you're trying to resolve in terms of angle measure here. All right, so now we're going to talk about using trig to solve right triangles. We're going to talk about what solving a right triangle means. Right, so solving a right triangle mathematically means numerically identifying all the side lengths and all the angle measures. So that means 90, 40, 50 for the angle measures in degrees, and then 6, 8, and 10 for the respective side lengths. And we can solve any right triangle, complete a right triangle's define lengths and side lengths and angle measures given any two side lengths or one side length and one angle measure, which is not the right angle. All right, so let's take the first example, two side lengths. We're going to use a Pythagorean theorem to solve for the third side. Then we're going to use inverse trig functions to find one angle measure. And then we're going to use what we know about the sum of the interior measure of angles in a triangle to solve for the third. All right, so we can see that we actually have a 5, 12, 13 triangle, or we can use a Pythagorean theorem to solve. And then we're going to use what we know about the relationships between the side lengths to solve for one of the angle measures. So we'll say the inverse tangent of the side opposite 5 over the side adjacent 12 is equal to the angle measure. And so if you calculate inverse tangent of 5 over 12, you'll end up with 22.6 degrees. 22.6 degrees leaves us with a balance of 67.4 degrees for angle B, because we know the sum of the measures of the angles in a triangle equal 180 degrees. All right, so now we can also solve a right triangle given one side length and one angle measure. Here we have one angle measure of 39 degrees and one side length of 7. So we're going to solve for CB first. And we know that CB, if I take the sine of 39 degrees, it should equal 7 over CB. So let's figure out what that means. And I've solved everything for you. The sine of 39 degrees is equal to 7 over x. Solving for x leaves us with x is equal to 7 over 39. And you solve for that and you get 11.1 as the length for BC. Right now we're going to use a different relationship. We don't have to, but we're going to determine that this angle measure is 51. We kind of skipped ahead to number 3. We subtracted 39 and 90 from 180 and we're left with 51 degrees. And so we're going to say that the tangent of 51 degrees is equal to an unknown value over 7. Or if we rewrite it, we can say 7 times the tangent of 51 degrees is equal to BD. And if we use our calculators, we can find out that BD is equal to 8.64. All right, so finally we're going to use trig to solve real-world problems. All right, so I have this gentleman, Ryan. He wants to throw something to Carter. Ryan's on the bottom floor. Carter's on the first floor. I know the height from Carter to the bottom is 20 feet. And I want to figure out the actual distance from Ryan to Carter and then the horizontal distance. So I'm going to use my trig functions here. I'm going to solve for y, the actual distance first. So I'm going to say the sine of 35 degrees is equal to 20 opposite over hypotenuse y, and then rewrite that for y as y is equal to 20 over sine 35, and that ends up being 34.87. And now I'm going to use this value, and I don't have to because I can use tangent, but I'm going to use the value of 34.9 to solve for the value for x. All right, so I'm going to say the cosine of 35 degrees is equal to x over the value that we just discovered, 34.9. And then solving for x, 34.9 times cosine 35 leaves me with a value of 38.6 feet as the value for the horizontal distance from Ryan to Carter. All right, so new problem. I'll let you solve this on your own. What we're looking for is the angle measure here from Ryan to Carter, is otherwise known as the angle of elevation, and we're leading into that topic. So you can solve for that angle measure. All right, so we know that the inverse sine of 20 over 45 is equal to some angle measure. If we calculate that using our calculators, we end up with approximately 26.4 degrees. All right, so that leads us into a discussion about angle of elevation and depression. Angle of elevation is the angle made with a horizontal and a line of sight. And the line of sight is just that connection between the bottom right here and the upper left, or the sight between what we are observing and ourselves as the observer. So in this case, the line of sight from the upper left to the bottom right is still this diagonal line, the observer and the observed, and then vice versa. If this is the observer and this is the observed, here is my line of sight. Angle of elevation is that angle made with the line of sight and the horizontal from the observer. Remember, it's always made with the horizontal. And the angle of depression is the angle made with the horizontal and the line of sight. Now we can use what we know about these horizontal lines. They're actually parallel lines, right? Because we know that alternate interior angles are congruent. Angle of depression, angle of elevation, in this case, are going to be the same. All right, so these measures you can use to find the angle of elevation or depression, but this value x here is not the same as this angle of depression. All right, so let's use what we know about angle of elevation and depression to solve for a problem. To an observer on a cliff, 400 meters above sea level here, the angle of depression to a ship is 42 degrees. We want to find out the horizontal distance from the base of the ship, base of the cliff to the ship, and the distance from the observer to the ship. Now the problem is we have 42 degrees here. Here's the angle of elevation, but it's not part of our right triangle. So we're going to use what we know about alternate interior angles to solve for this angle, and then use trig to solve for the rest. All right, so we figure out that this angle measure is 42 degrees here. This is the angle of elevation from the ship to the observer, which we can use to solve the triangle. 400 meters is still the elevation. Now we're going to solve for this direct distance here. So we know that sine of 42 degrees is equal to 400 over what we'll call y here. So y is equal to 400 over sine of 42. And we end up with a value for y of approximately 597.8 meters. And then we can also use a tangent relationship. Tangent of 42 is equal to 400 over 4, tangent of 42 is equal to 400 over x. And then if we solve for x, x is equal to 400 over tangent of 42. We end up with a value of x equal to 442 degrees. All right, this is a fun problem. I'm going to show it to you here, and then I don't have enough time to go through all the answers with you, but you can answer all those questions while I pause, and then I'll show you the answers. And that will be it for this edition of 9.1 Solving Right Triangles with Otten Math. So hold on a second. Okay, so the first question, how high does the roller coaster go to the top? We're going to use tangent of 23 degrees. So x, we're trying to find x is equal to x over 180. We solve for x. The vertical elevation is going to be 76.4 feet. And then what's the distance from the bottom to the top going up and coming down? So we're going to use our trig relation, or our Pythagorean theorem. Solve 76.4. We solve for the hypotenuse here, 195.5. And then we know this value here is 60 going down, 97.1. So we add the two together. That's the distance going up and then coming down. Okay, how far or how fast does the car go up? We know that it takes we're going at 8.3 feet per second, given that we've traveled 195 feet in 23.5 seconds. So 195 feet divided by 23.5 leaves us with 8.3 feet per second. And then how fast does the car go down? We know it takes 2.8 seconds to go down. We know that that length here is 97.1, so 97.1 divided by 2.8 seconds leaves us with 34.7 feet per second. So about 4 times as fast going down than going up. All right, so that's your problem solved. That's it for this edition of Otten Math. Hope you've enjoyed it. Lots of fun in solving right triangles.